All right, aloha to the last talk of the conference, Made in America. Well, until OBT5. So in this talk, Runa and I are going to tell you about some intriguing Mac malware designed by US government spy agencies. In this talk, though, we're also going to explain our individual approaches towards analyzing Mac malware. So hopefully you can kind of get a sense of how we approach these problems and perhaps apply some of these same techniques and approaches to your Mac malware analysis adventures. As mentioned, I'm stoked to be presenting today with Runa. Runa works on digital security for journalists and other high-risk individuals. Her current work builds on some very impressive experience at a time at the New York Times, Freedom of the Press Foundation, and also a project you might have heard of, the Tor Project. So I'm going to hand this over to Runa to dive in. Actually, one more slide, sorry. Get a little ahead of myself. So as noted, we're going to be talking about Mac malware that's designed by three-letter government agencies. So to start with, Runa is going to be talking about an implant that has been attributed to the CIA known as Green Lambert. Following this, I'm going to dive into Double Fantasy, which is NSA's first stage macOS implant. These samples will be available on Objective-C's website shortly, so if you want to download and play along, you will be doing that as well. One favor, if you hear any helicopters or black SUVs pulling up, let us know. Runa, we can sneak out the back and get out of here. All right, so no further ado, hand it off to you.
Cool, thank you. Thanks everyone for being here. Thank you to people on the stream for showing up. I know some of you are staying up late. Thank you to Patrick and Andy for organizing this amazing conference. And Patrick, I don't know how you do everything that you do, but I am so grateful for all of your time and your support and your encouragement during this project. So, jumping in with some history. So, back in March 2017, WikiLeaks published this project that it named Vault 7, a bunch of information that was stolen from the CIA and then leaked to WikiLeaks, and WikiLeaks then started publishing this, I think from March 2017 until I think November of that year. A good portion of it was this like internal confluence that then just has a lot of documentation about different tools that they had developed, about their development tradecraft, do's and don'ts, and a lot of that type of stuff. A lot of interesting stuff if you want to go dig in. About a month later, Symantec came out and then said that a lot of the information or some of the info in the Vault 7 leak that we've now looked at, the development documentation, the timelines, the dates, it sort of lines up with an actor that they're tracking as Longhorn. And the post goes on to sort of detail what they've found there. A day after Symantec, then Kaspersky came out and said, yesterday Symantec published this stuff. We are tracking the same actor as the Lamberts, and then went out to detail what they have found and what they've been tracking for some period of time. And so specifically the sample that I'm looking at here is the Green Lambert sample for OS X, which was then disclosed by Kaspersky back in 2017. If you read that post, it sort of details a lot of the different implants in the Lambert family. And so like got different colors, green and black, and I think there's white. Specifically though, green is the OS X sample, or the one that exists on Windows and OS X. So another thing that I did last year was that I dug into the development tradecraft do's and don'ts doc. So this spreadsheet is public, so if you want to see the different iterations between, I think there's like 52 different versions of the document that's now available, where they're talking about how they do what they do, what kind of guidelines they have for when they develop different cyber tools, what they should and shouldn't do. And I thought it was like pretty interesting to sort of look at what are the guidelines that a sophisticated actor would have for the tools that they develop. and then also look at that in the context of the Green-Lambert sample. The reason I find this so interesting is that when you're looking at tracking sophisticated actors, I think it's going to come down to more than just looking for an overlap in hash or domain or IP address. If you look at the work that Kaspersky did, and I don't have a date and time for this post, but finding an overlap between the Sunburst backdoor and Kazuar, it's going to come down to how the code is generating the victim UID or which algorithm they're using for some type of functionality or what kind of hash they're using to do a certain thing. So the overlap is not going to be in something like fairly easy like a hash or domain or IP. It's going to be in something more complex. So as I mentioned, Symantec had then said in their post that the information in the Vault 7 leak matches what they're seeing for what they're tracking as the Longhorn actor. And I was then curious to see if, like, is this true for Green-Lambert on OS X as well? Can we dig into that specific sample and then look at the development tradecraft? Is there anything there that lines up? Can we say that, yes, they follow their own guidelines? Is there something that stands out? What else is there in here? Quick note about victimology for the Lamberts, or Longhorn, which I actually can't see my own slides, so that's fine. There's nothing like super specific that's been mentioned about exactly how, in the context of the Green-Lambert sample for OS X, there's nothing specific that's been mentioned about exactly how you get infected with that malware, the type of target system, where in the world that system would be located. There's been talks across Symantec, Kaspersky, and researchers in China that the Lamberts has been known to target governments, for example. That sort of just gives you an idea about typical targets. There is a teeny tiny portion of the Symantec post that just highlights that at some point in time, an installer for one of the Longhorn tools was dropped and run on a system in the United States, and that sometime after, I think it's a couple of hours after, an uninstaller was then launched to remove it. So that just goes to show that they are probably trying to make sure they do not infect systems in the United States. This slide from Kaspersky just sort of shows the Lambert family malware. As I mentioned, there's like a bunch of different ones. Green, according to Kaspersky, is the oldest and longest running, and the only one where we've found both non-Windows and Windows versions. So the Kaspersky's post on this topic is great. So if you want to see how these all tie together and sort of which ones might have like handed over to another one in the development timeline, you should go check out that post. Okay, so for Green-Lambert for OS X specifically, this is, I have given a lot of talks over the years, but this is actually the first malware analysis focused talk that I give. It was something that I always wanted to dig into and learn more about, and given the pandemic over the past 2 years, I actually had more free time. So I figured I would take the sample and just figure out, well, what can I learn? What is there? So starting with just looking at the sample on VirusTotal, we can see that it was first submitted to VirusTotal from Russia in 2014 under the name Growl Helper. It was first detected in late 2016 by Kaspersky, and then about a month later by a security firm out of Taiwan, if I remember correctly. So if we download this file, like what do we get, right? We have the name Growl Helper, so we know that that is like the name that the binary gives itself on the system. Now, Growl is a popular, or rather was a popular notification system on OS X, first released in 2004, retired in 2020. If we look at the file info, we can confirm that this is a 32-bit macOS executable. It's not signed. It's fairly small. It doesn't have a whole lot of dependencies. So like at this point, that's sort of the info that I have, and I then try to figure out, well, what else can I dig into? So we can look at strengths. There's some interesting clues there that pop out. The first three reference login item, launch agent, and launch daemon, just different options for gaining persistence on the system. The next three, Google libevent and 1.3.a, I thought was really interesting because libevent is a event notification library that's also used in Tor, and version 1.3a was released in February of 2007. Now, Tor was open sourced in 2002 and developed by the US Naval Research Lab. libevent was developed by some of the same people. libevent today is really popular and used by like all sorts of folks, including Facebook, but I was surprised to see it used back then in this sample. Then there are some strings for like auto-determining proxy settings that I thought was pretty interesting that I'll get back to later on. And then the last two refer to something that was added to Xcode 2.2 and released in November 2005. So, and I'll get back to that in a bit, but this is what I just pulled out from just strings, looking at what's there, Googling a bunch of stuff just to see like what stands out. I also knew that I wanted to be able to run this sample at some point. So the question became like, which version of OS X would it need? So I used nm to dump all of the symbols. I just plugged that then into a spreadsheet, and I started just Googling every single one of them, just to figure out what they do. Mapped that into a spreadsheet, and also stumbled upon then a few that were deprecated after a certain version of OS X. That's not to say that it wouldn't work after that version, but it wouldn't be, it would be listed as a deprecated one. And so mapping all of that out, I found that this sample was likely then developed for or around OS X 10.7. And I've later confirmed that it will run on 10.8. Pretty sure it will run on any 32-bit system as well. But this is sort of how I then went about narrowing down which version of OS X I should get for my VM. So if we take all of these like dates and times and plug that into this timeline, we have 2004, Growl, the notification library comes out. We've got Xcode 2.2 comes out. We've got libevent 1.3.a comes out. You have OS X 10.7 and 10.8. And then you got towards 2014, 2015, 2017, this sample ends up on VirusTotal. Vault 7 is stolen. WikiLeaks releases Vault 7 a year after that. And that's when Symantec and Kaspersky and those groups publish their research. So if I had to say something about when this specific implant was likely developed and used based on the information that we have now, I would say sometime between 2007 and 2013. And we'll get back to that in a couple of later slides as well. So then the question was like, well, does it run, right? So I had narrowed down that it would likely run on 10.7, and luckily as of June of this year, OS X Lion is available for free from Apple. I tried to get it in May when it was like $20. Apple will happily take your $20, but not actually give you the downloader. So something that I also did was that I went on eBay and I spent $95 on a MacBook that runs Lion, just so I could actually run it on bare metal as well. Okay, so let's run it. Let's see what happens, right? So you can see that it persists as a launch agent. The implant also self-deletes, so having snapshots in your VM can be super, super helpful. Let's see, do I have a? Yes, I do. If we then look at the plist file that Growl helper creates, you can see that like you can see where it stores the binary. You can see that it takes a command line argument, and then you can see that it also has the run at load key set to true. which just means that every time this user logs in, this one is going to run, and that is how it persists on the system. Looking at file system usage, so another thing that I thought was really fun for this project was, sadly, none of Patrick's amazing tools run on 10.7. Maybe something to fix, Patrick, in your copious amount of free time. So I had to figure out what kind of native 10.7 tools will actually help me get this work done. So you can monitor file system usage with FS usage, and then see that Gradle helper will create a bunch of different files, a bunch of different folders. It will then do some cleanup. So you can get a pretty good feel for what it is that it is doing on the system. And in that, as you can see, it has a dot profile, dot bash profile, bash rc, and some other files. Then in one case, I also found that it created a dot profile in the current user's home directory with a path to Gradle helper, and the comment says automatic Gradle helper do not remove. And that will then run, if I remember correctly, every time the user opens the terminal. Is that right? Yeah. Cool. Thank you. I also found that there's a difference in how this one behaves on the system if you're online versus offline. So in the top example, that's when I'm online, bare metal, MacBook, actual hardware. And you'll see that the files created include Gradle helper, and then a second binary called software update check. In the bottom example, where I am offline, and in this case, when I mean offline, I mean a VM that is isolated and does not even have a network card. If it has a network card but is offline, I think you still get the software update check binary. So that's just a difference in what it does on the system when it doesn't have a network card. And I thought that was really cool. I was really, really excited, holy shit, this thing drops another binary. It's really cool, I'm gonna dig in. Very quickly realized that it just drops a copy of itself with a different name. So after talking to Patrick, theory is that it likely uses that then to check for updates for itself rather than try to do that within the Gradle helper one. As we saw earlier in the plist file, right, it had the -f command argument flag. There's a bunch of different ways you can go about finding command line args. My initial method was just try and fail, right? I had a VM, I had a snapshot, it was easy to revert back whenever I needed to. So let's just launch this thing with run through the whole alphabet and just see what happens. So I found some interesting bits and pieces. If you run it with -c, it just sort of prints commands will be processed immediately, and then it just waits for additional inputs. If you run it with -d, that's when it, if it's already installed, will drop a copy of software update check. Later on, I also found that it does run, in the plist, it has -f. But then if you run that and then look for what else it does on the system, it does also run itself with -d. So it does try to drop that copy. Then there's the -f, which is the default, and then there's some other methods where it, at least in my very isolated offline VM, will run without persisting, and then it varies in which files it creates. But if we then wanted to try and find the command line args in Hopper, you can then just load up the binary in Hopper, which is a fantastic tool, and I can't believe it's just $99. And just look for argc, argv, get-opt, and then click on the pseudocode mode icon, and it will then tell you right there that the supported args are C, D, E, F, L, N, P, R, and capital R, S. I don't know if all of them are implemented or if all of them will actually do something, but those are the ones that are listed in the binary. The Chinese research team also looked at all of the entry points supported by Green Lambert for OS X. There's, if I remember correctly now, there's like 20 that do like a bunch of different things for like how to persist, setting up different types of HTTP, proxy, SSL, generating the UID on the system, and those types of things that are in there. File system usage, so I mentioned that it creates a bunch of like files and folders. It also does appear to like clean up. So one current theory of mine is, since all of these run before the binary's main entry point, that it really just sort of like first, like once the malware hits the system, it just sort of runs and sets up everything that it could possibly want and need, and then takes the time to sort of figure out, well, what is it that I actually need for the system that I'm on, and then it sort of cleans that up. So you can see here that at one point it created directories for like dsinfo and com.apple.advanced, but then later deletes that. Decrypting strings is something that Patrick was very, very helpful with. Hopper has sort of done some of the heavy lifting for us here. So on the left-hand side, you can see that Hopper has figured out what the values for ECX, EDX, and EAX should be. And I know Patrick will talk a bit about encrypting and decrypting strings later on. So like, let's just say that for now, we know that the routine on the left there is a string decryption function. We can then, on the right, use the LLDB debugger to load the sample into LLDB, set the program counter to be the value that we need it to be for the specific string. We can then manually set the values for ECX, EDX, EAX, and then have the allow the malware to like continue to execute up until our breakpoint, which is right after where it decrypts the string, and we can then just print out the now decrypted string from memory, which in this case is hversion.txt. There's also there are places in if you sort of load this into Hopper and you scroll around, you'll see there are a bunch of places where Hopper has figured out all three values for you. So you can just sort of plug that into LLDB, and that's pretty easy. There are places where it will give you 2 out of 3, and you'll have to do some math to figure it out. Patrick, in his training, talked about writing Hopper scripts to automate this. Maybe I will try and look at that next. But this is definitely where I got pretty lost. As in, I learned to do something new, and I got a new string, and it was like opening a new little package, and I had no idea what would be inside, and I thought it was really, really exciting. And so I spent a lot of time in decrypting a lot of strings. These are some of them that I found, where it sort of talks about login.php, getconf, showphp, uploaders, key, header, all sorts of like interesting strings. But like I said, because it like appears to handle encrypted strings in a bunch of different ways, I have not yet automated the decryption process. So I know there is more in there to dig into. Some of the interesting strings that really stood out is one is no LP configured, where LP in this case likely refers to listening posts, which is a military, it's like an English military term for SIGINT or reconnaissance. It's also used by the NSA in their implants. There's a Vault 7 document that specifically covers listening post creation. So it talks about having base OS images that are then like auto-configured to be listening posts, which I thought was pretty interesting. As we saw, there were some like HTML, PHP text files. I was not able to access those text files. Kaspersky had noted that Green Lambert samples have 2 CNC servers hard-coded in their configuration block, a host name and an IP address. And I assume that that's going to be present in at least one of these files. The researchers in China had noted that Green Lambert talks to the listening post through login.php and getconf.php, and that it downloads follow-up code through getfile.php. So there's like a lot more interesting stuff here that we just like don't have access to, in part because this sample is so old. Another thing that I found digging around in Hopper, and I will try and speed up a bit so I don't run into Patrick's talk, was I found this like version string where it just sort of says version equals 1.2.0. In Hopper, I saw that it then like has this little like equal sign where I knew that the string above was version, and then Hopper had figured out that here's an equal sign, so we have version equals something. So then I hit X to see the cross-reference to see where else is this equal sign being used, and then decrypted those strings to then build out what may or may not be some sort of like config survey. It runs uname on the system, date and time, uptime, current version of, I believe, the implant, and I think there's more there that I just haven't like built out. If you run the sample on bare metal and then capture the traffic with TCP dump and load it up in Wireshark, you get the host name and the IP address of the specific implant, which is pretty cool. And I have some slides that dig into that as well. So once like, sure, great, like we have the growlupdate.com host names, like let's Google it, right? Let's see what we can learn about it. Turns out not a whole lot. Google suggested that I can search for how to bake a cake instead. I feel like I have done enough. Wayback Machine had nothing. VirusTotal said that this URL was first submitted back in 2016, so that's probably Kaspersky. But if you look at crt.sh, that website tracks SSL certificate issued for various domains. If you plug in this domain name into the site, you find that an SSL cert was created in October of 2013. That's not to say that the domain did not exist before then, but at the very least, we know that it was active in October of 2013 because a certificate was created for it, which I think is pretty interesting. And that does match what Kaspersky had said around Green Lambert being active in 2013 and the timeline that we created early on with all of those different dates and times, that this was likely developed and used sometime between 2007 and 2013. Kaspersky singled it, so that's great. Quickly looking at just the development tradecraft do's and don'ts, just to sort of go back to that spreadsheet and see was there anything there that like stood out. As Kostin at Kaspersky pointed out on Twitter, any type of malware that like follows those guidelines and has like C2 jitter and secure arrays and uses SSL and doesn't take up a whole lot of space on disk and is encrypting logs and encrypts strings, only decrypts them when it needs to, like at that point, it's already more interesting like than most like run-of-the-mill type adware or malware. In addition, in this binary, so for one, the full size is a bit over what the CIA would call ideal binary file size. Not that I don't think that means a whole lot in this case. The use of LP for listening post may be a CIA or US government specific term. It's at the very least an English term. Use of what is an English abbreviation for the days of the week. I'm not sure that malware authors in other countries would necessarily use that. And then also use of libevent back before it was cool. And then I wrote a blog post that has all of these screenshots, digs into exactly how I did what I did a bit more closely, and Patrick is hosting that. So thank you.
All right, thanks, Runa. Super interesting stuff. Now I'm going to tell you about a first stage macOS implant from CIA's sister, and in my opinion, far superior agency, the NSA. And like Runa's part of the talk, yes, the focus will be on analyzing the implant, but also I wanted to show you how I generally go about performing malware analysis. I'm not saying this is the best way, but this is my way, so there might be some tips, techniques that you can pick up along the way. So the implant I'm going to tell you about is something called Double Fantasy. Cool name. The Windows version was originally disclosed to us by Kaspersky in 2015. Two important takeaways from their analysis. First, they articulated the fact that the apparent infection vector was the use of 0 days. And they also illustrated how this implant fit into a multi-stage cyber espionage operation, specifically as a first-stage implant whose goal was to confirm that the victim was of interest, and if so, install a more comprehensive, persistent second-stage implant. I do also want to point out that their analysis focused on the Windows-specific variant. At the time of the analysis, Kaspersky did not have access to a Mac version of this implant. However, they were able to sinkhole various command and control servers that the malware was beaconing back to, and they did see macOS user agent strings, which led them to believe, as they articulated in the research that we have on the slide, that yes, indeed, a Mac variant existed somewhere in China. Turns out a macOS version of Double Fantasy had been submitted to VirusTotal all the way back in 2014. Yes, from China, but had remained undetected by any of the antivirus engines on VirusTotal until 2020. Yikes. So the submitted file was named MD Worker, which mimics an Apple binary that is often found running multiple times on a normal install of macOS. So the idea is the attackers were likely hiding in plain sight. If we triage the binary, that's normally the first step I perform when analyzing a new piece of malware, we can see that it's an unsigned 32-bit Mach-O binary, which for binary, circa 2013, is the standard or the norm. Also, if we use OTool to dump its dependencies, we can see that it's rather self-contained, which is an interesting observation as well. As Runa mentioned, it's really good to run the strings command to see if there's any embedded or strings that we can pull out from the binary. A lot of times this can reveal a lot of the capabilities of the malware or guide your continued analysis. On macOS, we can use the aptly named strings utility. Make sure you run it with the dash flag, otherwise it only scans for strings in certain sections of the file. As you can see, though, on the slide, unfortunately, the majority of the strings in the implant are encrypted. This is not surprising. The NSA is not stupid. They realize that if and when their malware gets detected and discovered, it's going to be comprehensively analyzed, and so they're going to at least encrypt the strings to make this slightly more difficult. Now, it's always good to try to uncover the plain text values of any encrypted strings before continuing on with your analysis. Such strings can really help guide and simplify your analysis. So we're briefly going to go over one approach to how you can tackle the problem of encrypted strings via a disassembler script. Most disassemblers support the ability of scripts or plugins. I use Hopper. It's a great macOS-specific reverse engineering tool, so we're going to focus on that, but a lot of the concepts apply to other disassemblers as well. So in 4 easy steps, what we're going to do is we're first going to write a disassembler script that looks for the start and the end of the C string segment. This is where all the encrypted strings that are embedded in this binary lie. We're then going to programmatically extract each of these encrypted strings. We're then going to run these through the decryption algorithm, which we first have to identify in the malware and then re-implement so we can decrypt each string. And then finally, we're going to annotate the disassembly with the now decrypted string so that our analysis can be simplified and continue onwards. So let's go through each of these steps. I hope this is illustrative of how to write a Hopper script, but also how we go about decrypting the strings in this interesting binary. So first up, we need to find the C string segment. As I mentioned, this is the segment in the macOS executable in this specific binary that contains all of the encrypted strings. So Hopper provides a myriad of APIs to interact with the disassembly and parse through the macOS header. So this is pretty straightforward. As you can see on the slide, we simply iterate through all the segments and their sections, looking for one that matches __ C string. And then once we find a match, Hopper provides information about that section, including the start and the end. So now we have the beginning and end of that section, which is where all the encrypted strings are. Now what we're going to do is we're going to iterate through that section byte by byte, extracting anything that looks like an encrypted string. Lucky for us, these are all null terminated, so we can basically just read forward until we find a 0 and then assume essentially we have a null terminated string. And then do that until we reach the end of the segment. As I mentioned, for each of those strings, we're then going to invoke our custom decryption routine to decrypt the embedded string. Now, of course, in order to do that, we have to understand how the malware has encrypted and how it decrypts the string for its use. How do we find that? Well, it turns out fairly easily, and this is a generic approach for analyzing essentially any malware sample that utilizes encrypted strings, if you're interested in recovering the decryption algorithm. Basically, what you do is look for cross-references where the encrypted strings are used. Obviously, the malware has to decrypt the string before it's using it, and normally the decryption function is implemented in a standalone or helper function. So as we can see on the slide, there's an encrypted string that's passed to a subroutine called sub-D900. And if we look at the cross-references for this subroutine, we can see it's called every time an encrypted string needs to be decrypted. So it's a likely candidate for the decryption string algorithm. If we look at it at a disassembler, as we can see on the slide, it turns out, yes, indeed, to be the malware's decryption algorithm. We're not going to go through all the disassembly, but in short, it's a multi-key decryption algorithm that uses the XOR encryption scheme. So now we've uncovered the malware's encryption and decryption algorithm. What we can do is we can re-implement that in our disassembly script so that we can programmatically decrypt any encrypted strings. Pretty straightforward to do once we've understood the algorithm. It's about 15 lines of Python. We init the XOR keys. The first XOR key comes from the encrypted string itself. The second one is hard-coded to 47. And then what we do is we just iterate over each byte of the encrypted string, applying the decryption XOR keys. End result is we will have the decrypted string. Now we have the decrypted string. As I mentioned, we want to annotate the disassembly so that our continued static analysis is made easier. Hopper provides APIs to add inline comments, for example, where the encrypted string is. So that's the first thing we do. But we also want to add a comment containing the decrypted string at every location in the disassembly that has a cross-reference to the encrypted string. Luckily, Hopper has an API that gives you all cross-references for a given address, so we can resolve those and just iterate over each of those, adding the decrypted string as a comment now in that segment of code. So as we can see on the slide, the first encrypted string decrypts to /temp. We add that as a comment to the location of the encrypted string, and anywhere else in the code that encrypted string is referenced. Turns out the malware utilizes a second decryption algorithm for other strings. We can follow the same approach, look for cross-references. Turns out this decryption algorithm is even simpler. It's based on some multiplication. So again, we can re-implement this in Python in our disassembly script and pass any encrypted strings that are encrypted with this second encryption algorithm to retrieve the plain text values. So what do we have once we decrypt the strings? Well, some very interesting things. Recalling again that generally encrypted strings are the sensitive strings that the malware authors want to hide from analysts such as ourselves. First, we have something that looks like command line arguments passed to perhaps getopt. We then have some key value pairs that might indicate the use of a config file. We have a path to a CStore file, which we're not sure what that is. Looks like we have something related to command and control or LP comms. And then some strings that indicate the malware might be proxy aware. Also, we have more encrypted strings. Turns out there are a large number of sequential strings that appear to be related to a survey. This is unsurprising because recall that this implant appears to be a first stage implant, as I mentioned, whose main goal is to kind of figure out if a system is of interest to the agency. And then we also have this DYLD insert library string, which we might be familiar with it in dilib injection attacks. Not sure why that's in, but it turns out to be rather interesting. Now, once I've decrypted the strings, I Google them because it's often a good time to figure out if other people have already analyzed this sample. Perhaps it's brand new. Well, one interesting match that actually I found on my file system was that Apple's malware removal tool actually has a signature for this binary. Apple is very notorious for updating their antivirus components of the operating system without giving anybody any indication that A, they are doing it, or B, what they are looking for. So if we reverse engineer this specific component called MRT, or the malware removal tool, we find that Apple has a signature that looks for that CSStore file. Interesting. If you Google this file, there are no other hits. So no one's talked about this macOS implant publicly before. Also, though, there are in that same signature some paths to persistence, and also Apple's name, OSX ATG11.A. So, hey, I guess now we know what that internal signature name matches to. In terms of the persistence, we didn't actually see those strings in this variant of the binary, which likely means that the NSA had or has multiple versions of this binary, some that persist and some that don't. The variant we're talking about today does not appear to support persistence functionality, which again kind of makes sense. A first stage implant, especially that's just designed to survey the system, doesn't really need to hang around or persist. So now we want to find the malware's entry point, right? We've done some static analysis, we've decrypted the strings, we've ran OTool, we've basically triaged a sample. It's now time to dig into the disassembly. So how do we find the main entry point? Well, if we use OTool, we can print out the load command that specifies where the operating system should kick off execution within the binary. We find an address, but if we go and disassemble that address, that just turns out to be C runtime code, not really the malware's main function. However, if we trace through this code, eventually we find what is the call to main. And we know it's main for several reasons. If we look at the arguments, they contain the standard argv, argc arguments that are passed to the main function, and also then is followed by an exit. This is kind of the standard way that main is invoked. So now we have the malware's main function. This is where the malware authors begin their logic. First thing we do is we can see they decrypt the string /temp thanks to our Hopper disassembler script. We already know this, that is what it's going to decrypt to. It then changes the directory, invokes a subroutine to parse any arguments, installs some signal handlers, daemonizes itself twice, and then invokes something else. So let's dig into each of these subroutines. As I mentioned, one of the first thing it does is it parses any command line arguments, recalling that the command line arguments were an encrypted string. When analyzing a malware sample, it's interesting to see what command line arguments it supports, because this can show you some functionality or the capabilities of the malware. A lot of times certain code blocks will only be executed in the response to certain command line arguments, so you want to figure out what those are so that then you can dynamically instrument the malware to go down those paths. So if we look at that, we can see, as I mentioned, it decrypts the string of the supported command line arguments, CDILSP. It then invokes getopt to parse these, any command line arguments that have been passed in. But interestingly, if we look at code after the call to getopt, it only has logic for the C and D methods. If we look at what C does, it decrypts the string hello and prints that out, and then invokes a subroutine that decrypts the path to that CSStore file, deletes it, and then calls exit. The case for D, it simply exits. We can confirm that our static analysis of the -C command line argument is correct by running it on an isolated VM while monitoring it also with a file monitor. We can see that indeed it looks to see if that CSStore file exists, and if so, it deletes it. So again, the C command line argument seems to be a cleanup. So here's a table that summarizes the command line arguments. C-C is cleanup, -D is die or delete, and then the -I, L, S, and P are not implemented in this sample. This is interesting because it indicates, again, that there are likely other variants of this sample, but the malware authors were smart enough to compile those out, right? They might have variant A, B, C, and D. Version A doesn't need to persist, so they decompile out the persistent code. That's actually a kind of a hallmark of a sophisticated adversary or a project that's well engineered. Unfortunately, though, they didn't change the string of the supported command line arguments, so we can see that they are interested. I've kind of guessed to what the names are. I might be interactive, L might be how you specify a listening post via the command line, P might be how you persist, etc., etc. I mentioned this binary also daemonizes itself, and it does this in an interesting way. Specifically, it calls fork twice. I had no idea why it did this, so I went on Stack Overflow and also talked to Jaren, who's kind of the process guru on Linux and macOS, and we basically came to the conclusion is this is actually the way to legitimately daemonize yourself so you're not attached to a terminal or a TTY. So, again, if you really want to be kind of extra stealthy when you're daemonizing yourself, this is the correct way to do that. So again, these malware authors really know what they're doing. Now, we've talked a little bit about that CS store file. So I was like, okay, we got to figure out what that is. So I looked for cross-references to that, and early on in the initialization logic of the malware, it called a subroutine that decrypted the path to this file, then passed it to another helper file, which opened it, read it in, and then decrypted its file contents. If we create that file on disk for the malware and then execute it in a file monitor, we can see, yes, exactly, it is indeed opening and reading the data. If we look at what it does once it decrypts the file, it parses through looking for all these key value pairs that themselves were decrypted. But since we can decrypt the strings, we can recover what the key value pairs likely are. There's a large list. I have no idea what the majority of them are, but we can make educated guesses for some. For example, LP is likely the listening post, which is how the US government generally refers to a command and control server. If we look at Kaspersky's documentation for their analysis of the Windows variants, they mentioned the fact that this malware has command and control servers, or LP servers, in a config file. So it makes sense that the macOS version likely implements that as well. Unfortunately, though, I did not have access to a config file, so I couldn't dig too much deeper into that. Speaking of command and control and talking to an entry point, it's always kind of interesting to understand how a malware communicates with that server. If we reverse engineer the malware, continue our analysis, we find that it utilizes an open source HTTP and WebDAV library called Neon. There's embedded strings and code that match that project. Interestingly enough, that project is GPL'd. I'm not sure on the GPL rules, but my understanding is if you use a GPL project, you have to ship the source code as well. So maybe we can call our friends up at the NSA and tell them, hey, y'all have to release the source code now. We'll see how that works. One interesting thing, though, is that this library is A, cross-platform, but B, also supports logic to handle authenticating proxies. A lot of times, intelligence agencies' targets are rather security conscious and will be sitting behind authenticating proxies. This means if these intelligence agencies get their implant installed on one of these victim systems, perhaps with a zero-day exploit or some supply chain interdiction, well, that malware better be able to talk through an authenticating proxy, or it's not going to be able to beacon out to the command and control server for tasking. So not something we see very commonly, especially in Mac malware, but in both the sample I'm talking about and the sample Runa talked about, the support for authenticating proxies is quite, in my opinion, notable. Now, as Kaspersky mentioned, the main goal of Double Fantasy, the Windows version, is to validate victims and confirm that they are interested. Looking at the decrypted strings, we saw a lot of strings that appeared to be related to survey logic as well. We see these sequential strings starting at 001, going up to 48, and some of them decrypt to values that appear to indicate a survey. They're all contained within one subroutine, so I wondered, could I coerce the malware to essentially perform a survey for me So A, I could see how it performed it dynamically, but B, also see what the survey contained. The answer is yes, of course. We basically just load the malware in a debugger and then manipulate the instruction pointer to point to a function that calls the subroutine. If we then execute this subroutine, it turns out that once it's done surveying it, it returns the survey, which if you took the training or you're familiar with malware analysis and reverse engineering, you know the return value of a function can be found in the EAX or RAX register. So as we can see on the slide, in a debugger, once that survey function returned, I could simply instruct the debugger to print out the value of the RAX register to see the survey of the system. And we can see it's a fairly comprehensive survey, right? It's gathering information about the system, the infected box, network information, user information. It has a timestamp of when the survey was run, which you can see was Saturday night. This is how I spend my weekends, reverse engineering malware, but isn't that the dream? Also, we can see the name of the user and the name that the malware finds itself running. And again, this is then all sent back to the listening post, so readily the listening posts or perhaps analysts who are studying this malware can quickly ascertain if this box is of value and then, as we mentioned, likely install a second stage implant. So backtracing from the survey logic, I wanted to figure out if this was something that was tasked or if it was something it would do automatically. So looking backwards in the disassembly, I found what I believe is the logic that handles the commands from the listening post, the tasking. So there's a lot going on this slide, but the main takeaway is that it gets a value from the server, the listening post, the command and control server, and it uses that to index into a jump table that has offsets for all the code blocks for each specific command. And we can see that there are 53 hex, which is 83 decimal command options that it supports. A lot of them, though, are not implemented. If we look, for example, at the offset for 21F, we can see it simply returns, not implemented. For the survey one, though, we can see that what we do is that turns out to be command OX1E. If we take that and grab the offset from the jump table, we then find the logic which implements the survey, which is the subroutine that we just saw. And again, this is how I uncovered this jump table. So this is nice now because now we find the code blocks for all the commands that are supported by the implant that can be remotely tasked from the command and control server or from the listening post. So we're not going to go through all these commands, but let's touch on a few of them. First up, we have command 9. This apparently reads a file from the file system and then sends it back to the command and control server. Basic file exfiltration. Again, this is something you expect to find in a lightweight first stage implant, perhaps to collect some files to help ascertain the identity of the system. Also, though, if we look at the APIs that are used, they're all very Linuxy. They're not using the Apple-specific Objective-C runtime file I/O methods. So again, this kind of indicates that the malware authors were more familiar with Linux and then maybe ported this over to macOS. And there's a lot of indicators showing that, yes, this was the case. Also then we have command OX50, which is rather interesting. It's a download and exec command. This isn't that novel or unusual, but this is something we expected to see. As we mentioned that once this binary has ascertained that this is a box of value, that the intelligence agency likely installs one of their more comprehensive, sophisticated second stage implants. So obviously, this first stage implant is going to have to implement that download and execute logic. So we find that in command 50. We can see they download a file from the internet, and then they chmod to set it to be executable, and then they execute fork in order to execute it. Now, one very interesting thing is that before they call exec to exec this second stage payload, they actually unset any DYLD insert libraries. And this is because environment variables are passed from the parent to the child, and they don't likely want to spawn this second stage implant or second stage payload with these DLYD environment variables set. Why this is interesting is this indicates that there is some mechanism where the parent process, the implant itself, could be executed or persisted using these environment variables. which is a very stealthy way indicating that perhaps it was injected into another process or persisted in a very stealthy manner. As far as I'm aware, there's not any other Mac malware that widely utilizes this approach. If we go back to Kaspersky's report, we can see that they say that the double fantasy malware on Windows uses a technique known as DLL COM hijacking, which is conceptually similar to dylib hijacking, which you do via the DYLD insert library methods. So we don't have more information about this, but this is kind of a breadcrumb that shows that they are using other sophisticated and rather stealthy techniques to either persist or inject the malware using these environment variables. But again, that's not implemented in this version, but they didn't compile out this code, so we can, essentially figure that out. All right, so let's wrap up this talk before the black helicopters show up. Some conclusions. First, really not surprising, but your favorite or not so favorite US government intelligence agency has Mac capabilities, even going back decades. This is really not surprising. Second, we've really saw that the Mac variants of this malware often mimic, at least in terms of functionality, their Windows counterparts. Windows, Linux, et cetera, et cetera. This is not surprising. If you're an agency that's infecting a large number of systems around the world, in order to scale and manage those, you want all your implants to have the same functionality. So you can deploy them to Windows, Linux, and Mac systems, and then command and control them all from one listening post. Thirdly, these tools are impressively well engineered. I always say malware is simply software with malicious purposes. As Thomas talked about earlier today, a lot of the Mac malware is kind of crap or shit, in my opinion. If you look at this malware, it's not overly complex. That is by design. It's a simple first stage implant, but it is engineered very well. The malware authors have a deep understanding of operating system internals. They write excellent software, and this is, something that's rather unusual. Also, things like leveraging environment variables, taking into account authenticating proxies. They really understand their targets, especially considering a lot of their targets are security conscious. So hopefully this whetted your appetite for analyzing Mac malware, especially that written by three-letter agencies. But also, if you're like me, you might be wondering, where's the newer stuff, right? This is from like 2013, used maybe up to 2015. That's like 5 or 6 years ago. Hopefully, though, the information we provided today, a lot of this analysis is, being discussed first time publicly, especially around the macOS variants, will maybe lead us to these newer variants. So stay tuned. Maybe we'll have a talk about OBTS at OBTS 5 about that. Fingers crossed, we will see. So that's a wrap. Just some resources on that. There's some other great resources, especially that dig into the Windows counterparts. So if you're interested in digging more into the malware, it was important to include those as well. We have a few minutes for questions and answers, or questions and hopefully answers. Yes?
On the decryption strings, I've never used Copper very much, but I know that like Radari will allow you to emulate instructions. Is that something that I can do with Copper? Like instead of re-implementing the decryption function, you can just, pull all that code and let it emulate it on a set of the decryption strings?
Yeah, and that's actually, so the question was, could you use instruction emulation to decrypt the strings? And the answer to that is yes. That would actually be a good approach if the malware was leveraging perhaps a more sophisticated decryption algorithm. This one worked really well because it was a very simple XOR multi-key, so it was trivial to implement in Python. If they were using some, NSA custom crypto, exactly. It would have been far more efficient to essentially emulate those instructions or take the approach Runa did, which was to allow the malware to essentially decrypt itself. So yeah, I like that you brought that up because there's always multiple ways to analyze malware with pros and cons, sometimes depending on the complexity of the malware. The reason was I was like, I've never written a Hopper script before. Like, this is a perfect case study. And I was like, this is fun. I have a weird idea of fun, but yeah. All right, any other questions? Awesome. If not, we are going to now wrap up the conference with some endnotes and some prizes. Hooray.